Okay, recording has started.
Okay, so this is basically our second meet on number 3. So most of the topics that we'll be discussing in this meet will be related to primes, basically uh, integer factorization, how to find primes, sieve, and we'll be doing a lot of problems on those topics basically. Okay, so I hope I'm audible to everyone. So let's begin with integer factorization. So the basic question regarding integer factorization is suppose you are given a number n, what is the most efficient way to find the factors of that number n? So here should be- hmm. So uh, uh, journal fits. एक सेकंड मेरा स्क्रीन दिख रहा है क्या?
Yes, we can see your screen.
Okay, excellent. Journal company का हाँ, so अरे मेरा जर्नल काम नहीं कर रहा है.
वो यूज एक्स इनपुट को अनचेक करना होता है शायद से.
No.
जैम बोर्ड पे ट्राई करें या फिर
ये डिटेक्ट ही नहीं कर रहा.
हाँ अब चल रहा है.
हाँ, but this will be weird. Okay, so basically suppose we have a number n. The question is basically what is the most efficient way to find the prime numbers, the factors of that number n. Okay, so one basic way that we can do to find one simple way that we can do is basically we can iterate through all numbers from 1 through n, and if they're divisible by, if they divide n, then we basically put them into a basically array of factors. Okay, so yeah, so that will so the complexity of that algorithm will be order of n, right? But can we make it faster? Like, can we make this algorithm faster? Well, so indeed we can make it a lot faster by considering only factors till root of n, and if they do divide the number, then we just check whether the counterpart of that also divides the given number as well. So mm, yeah. Huh. So suppose, yeah, so as you can see here, so suppose I have a number say n. What I do is that I iterate through square root of n, and then I check whether that number is divisible by d, and if it is divisible, then I put it into my required array of factorization, because it is a factor, and then I check whether upon dividing n by that factor, if that's equal to that the same factor as well. So we can have a number say 4, which can be represented as 2 squared, and you don't want 2 to arise 2 times, right? You don't want because both of them will be equal, and you don't want 2 to come as factor twice. So we will only consider distinct factors. That is why we have to check this, and then we just push back our required new factor there as well.
Could
So
you, one second, could you repeat why are we checking D not equal to N by D?
yeah, so suppose you have your n is 4. Okay, then what are the factors of 4? 1, 2, and 4, right? Nothing else. Makes sense. So suppose I'm doing till square root of 2. So suppose I'm doing up to 2, so it will be d is equal to 2 to d is less than equal to 2, so it will d ka value 2 aega in the beginning. So now you check whether 4 is divisible by d, that is 2. So here my d is equal to 2, right? So this will be true. As a result, I'll push back d into my factorization array. So now my factorization array consists of two things, 1 and 2, because 1 is taken initially here.
It's just
But
to remove duplicates. Basically, you will have, if d is equal to n by 2, you will have two same values. Just to
yeah,
remove
so
duplicates.
if we don't check this, again n by d will give me 2, and 2 will again enter in the same array. So we don't want repetitions of same factors. We want distinct factors only. So that is why we just need we need to put this check, so that yeah, so that square numbers can be avoided or similar. Yeah. Does that clear your doubt?
Oh, how will we get the repetitions? I don't. Why would there be repetitions? We are iterating through from 2 to square root of n. So
Yeah.
we are only inserting 2 once, right? Where is the repetition here?
No, no, no. Check. Square root of n will be 2, right? Because n
Yeah,
is 4. Huh. So my d is 2. Makes sense? So
yeah,
n mod 2 will be 0. Then 2 will
yeah,
enter in my factorization algorithm, in my
yes.
factorization ka vector, right? Now, suppose this is not there. Then I'll
Hmm.
again put 4 by 2, which is 2, again into the same array, right? I'm getting two twos. Makes sense?
Why would you put 4 by 2 in the same array? We only want to find the factors, right?
Yeah, but if we only put d inside, then we won't get the factors which are bigger than square root of n, right?
Oh, so you want the complete factorization, not just which factors are present.
I want every single factor of n. So suppose n is equal to 8.
So you want exponents of primes also.
I want every
Yeah,
single
yeah,
factor.
yeah.
Yeah, 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 yeah.
Not just
Not just prime factors. No, no, no. I want every possible factor. So I
Okay,
want,
okay.
yeah, yeah, yeah. So I want every possible factor. That is why I have to do this. Yeah. So well, you can see this is order of O root n. But yeah, but this is a bit bad way to solve this problem. I can make it a little bit faster. So if I want to make it a little bit faster, not a lot, then what we can do is that we can use a different algorithm, uh, which will look like this. Yeah, yeah. So now what do I have here? I have yeah, so here I have again the same thing. I'm going to square root of n, because this is basically square root of n, and then I check whether it is divisible. I put it. But now this time what I do is that I divide n by the same factor. So like if 4 comes, then the 4 gets divisible by 2, divided by 2, and then again I check for this, and like I put it in the factorization. So this loop basically is a smart way to reduce the previous algorithm that I showed you. And this is also order of O root n. But it will work in some cases a bit faster, but both will be more or less equivalent. Another approach that you can take, if you have already figured out primes, like suppose you have a list of primes, you can make it a little bit faster, just iterating through primes rather than looking through all numbers from this to that. So if you look through all the primes, you can check whether if your prime ka square is bigger than n, then it does not make sense because it will not divide. And then you just do the whole algorithm back again, like you divided it, you check whether it is divisible by my prime, and then you divide it by the prime, and then you put it back into the vector. So yeah, this is basically a simple check to see whether, like, since I am already pushing back one before, I don't want one two times. So this is, you can ignore this. Yeah, so these are 4 algorithms which you can use to find factorizations, and all of these are basically naive approach. Later, when I show you how to do sieve, how to use sieve of Eratosthenes, you can probably come up with an even better approach, which will work relatively faster. So now that we know about factorization, a basic question that you might ask is how to find primes, like how to test for primes. Suppose, like, I have a number p, I want to know whether this is prime or not. Now, you can find out several divisibility arguments. You can figure out several divisibility arguments and iteratively check everything and figure out whether something is prime or not. But like an exhaustive algorithm that you can use to find whether it is prime or not is that you will you will basically use the previous similar algorithm to the factorization. You'll again iterate through square root of n and check whether it is divisible by any number in between. So that will give you, so if it is divisible, then for sure it's composite because it is divisible by a number below it. If not, then it will be basically prime. So you get a very simple algorithm like this, which probably you have already know and you have been taught in basic classes, yeah, whatever. But like, yeah, so this the complexity as usual is O of root n. But yeah, this is the most simplest algorithm that you can think about to find primes. However, this is not always the optimal, and you can get much more faster probabilistic algorithms as well as deterministic algorithms. Although there are no proper deterministic algorithms, they depend on certain conjectures which are still unsolved. But yeah, we'll cover a few of those algorithms later in the meet. But as of now, this is the most basic algorithm you can use to find check if a number is prime. So now, question that you might ask is how to like how to find primes. Like, okay, I know how to check primes. I know how to check for primes, but like, what is an efficient method to find primes? So one second. You can see my screen, right?
Yeah.
It's showing Notion ka blog, right? Amul.
Yeah.
Uh-huh. Yeah. So this is an age-old problem in number theory, like how to find prime numbers. And this is one of the oldest known algorithms for primes, and it was discovered centuries ago by a Greek mathematician called Eratosthenes. So how it works is basically as simple as this. So as you can see in this GIF, what it is basically doing is it is considering the first number. So I'm considering that every number in the entire number system is prime. Okay, I'm starting from 2 because yeah, and then I am going through like this, like I am iterating throughout all the possible numbers that I have in my number series. And what I'm doing is that I am cutting off all factors of 2, or since 2 is the first number, from square of 2 to the limit I want, like n or whatever. Yeah. So I don't care about the ending for now, but like this is how the infinite sieve works. So 2, because 2 is because we are considering 2 to be prime, we strike off 4, 6, 8, 10, and everything following. So every even number is crossed out. Now the next number that we go through is 3. So now in this case, 3, as we know, is a prime for now because yeah, we have initialized it in such a way, and 3 is not divisible by any number before it. So 3 becomes a prime, and now we'll go from 3 squared to for the infinite sieve to infinity and cross off all divisors of 3. Now, one question that you might ask is that why are we starting from 3 square or 2 square, or like for any prime to be generalized from p square to the end? Well, if there is a prime if there is any number which is composite before p squared, then that composite number must be divisible by a lower prime than p. So for example, we can take 6 for the case of 3. 6 is divisible by 3, but it is already struck off because it is divisible by 2, a prime lower than 3. So I don't want to I don't want to increase my time complexity by going through distinct primes. And how I will do it is basically starting from 3 squared, and then I keep on adding, and then I keep on cutting off all divisors, all multiples of 3 in the form like I start from p square, then p square plus p, then I strike off p square plus 2p, and so on. So then if we keep on iterating, we see that 4 is already a composite number. We go to 5, then we see that 5 is a prime, and then we cut off again from 25 to 25, then 30, then 35, and we keep on doing this, and ultimately all composite numbers throughout the number series will be struck off, and the only things that will remain marked will be your prime numbers. So can you guess like a suitable algorithm to figure out based on what I have told you right now to find all the primes from for a given segment from 1 to n? Like what will be a suitable algorithm? This is basically for the infinite case. So how do we just morph it into for a given segment from 1 to a certain number n? And like what will be the time complexity? I don't expect you to like find the time complexity, but like an approximation, like what do you think it will be? Anyone? I suggest you don't. It will be better like if you guys just speak out rather than writing in the chat, because yeah, like I can then listen rather than like checking it multiple times. Like, it'll be easier.
You can just perform the same thing you showed, and considering only the numbers till n, right?
Yeah, I will keep on doing that till n. So any
So
case on
one,
that, tell.
no, so from 1 to n, you consider everything prime, and then you just check off everything until you reach root n.
Yes. Why root n?
Because anything after that would already have been marked by the ones before it, right?
And the ones that are not marked is by default prime.
Yeah.
Right. So can you guess like what will be the time complexity? It's
Some root n log n.
not exactly. It's not. One thing that is for sure is that it is certainly less than n squared, right? That is obvious.
Yeah.
That makes sense, right? But finding the time complexity is relatively non-trivial, because you use a theorem called the prime number theorem to show that how dense primes are. So a huge problem in number theory is that we don't know how primes occur. So I started with the quote by Euler, which says like human beings will maybe never penetrate and understand like how primes occur in the number series. But like, yeah, so we figure out we figure out a approximate density of primes that occur from 1 to n, and then based on that we perform our complexity analysis, and it comes out to be order of n ln n. So this is quite fast, but it can be made even faster. So later research has shown that you can get different types of linear sieves, which will also show later. But like, yeah, for now, this is one of the very efficient algorithms to find prime numbers.
Arjo, your Wacom is not working, right?
No, my Occam is not
So
working.
like if you guys want, I can show you the proof for this complexity. Like
Yeah,
if you haven't understood this, like you can write in the chat if you want me to explain the
हाँ अमूल तू एक बार दिखा दे, मैं Wacom fix करने का try कर रहा हूँ.
Okay, cool.
I'll stop sharing.
Okay, so can you guys see my screen?
Yeah.
Okay, cool. So the algo for Sieve was like we move to every number, check if this is prime, and if it is, we cut all the factors of it. So the approximate code of for this will be for int I equal to 2, I less than n, I plus plus, and for int j equal to 2i, j less than n, j plus equal to I. And we will only do this when we know that I is prime. So is prime I. Please ignore my handwriting. So yeah. So we just need to figure out how much time this loop will run. That will be the time complexity of this algorithm, right? So from this you can see
Wait,
that, yeah,
why is it 2i?
because
And
yeah, we can just start from I square also. It doesn't matter.
I squared, yeah.
Yeah.
both of them can be made to root n by doing I into I, right? In the first loop also.
And the first loop also. Wait a minute.
Yeah, so usually you don't just want to like have an array which can tell you if a number is prime or not. You also want the list of primes. So if you want the list of primes, you have to iterate through everything. If you stop at root n, you'll only get primes up till root
Okay,
n, but
fine.
you'll still determine which ones are the primes.
Okay. Fine.
Yeah. So like in the end, you have to once iterate through from 0 to n to figure out how many primes you have and like push back that into the vector. Yeah, so like time complexity has to be of order then.
Yeah.
Yeah.
Okay.
Yeah.
I didn't get this part. Iterating till root n should be sufficient to identify all primes, right?
Yeah, but suppose you need a list of all primes up till n, you don't have that, right?
You do, right? Because we've crossed out from till root n, we'll cross out all non-primes, right? Till
No,
n.
you have an array where you can like is prime array, your is prime array will be filled, but if you like want to iterate through all the primes, you'll have to like iterate through the whole n elements for all the primes. Like I mean, yeah, that's not much of a efficiency gain, but yeah, if you have a separate vector of primes, like for it can be for any number of reasons that you want that.
Did it make sense? Did you understand like why we are doing that?
I'm
But
no,
I think
actually,
if we still iterate till root n, the complexity is still not root n log n. It's n log root n. Like if I just show you, uh, we can just analyze the complexity, right? 1 minute. Let us analyze the complexity. I think it's not still root n log n. So what will be the complexity? When we are 2, we will move to we will perform n by 2 operations. Sorry, according to you guys, if I start at 2 square and I move to 2 square plus 2 and so on, so it will be around okay, 2 square, right? So for 2 I will move to 2 square comma 2 square plus 2 up till n. So what will be the time complex? Okay, how many operations is this? Okay, let me just analyze this for. Okay, let me just try with starting the inner loop from j equal to 2i, not I square, for now, so that I can just okay. So for 2, it will be n by I operate n by 2 operations, right? Because I am moving from 2 till n, and I am incrementing. I am taking steps of 2. For 3, it will be n by 3. I am moving from 3 till n. Considering now that I start from the inner loop from j equal to I and not j equal to I square. I will take this case also, but first let me begin with this. So if I start the inner loop, so the overall complexity, if I it will be n by 2 plus n by 3 plus n by 5, because we are only considering primes, up till n by some prime, which is p, let's say p is less than n for now, not root n. Okay, so the complexity of this is n star 1 by 2 plus 1 by 3 up till 1 by p. So this comes out to be equal to the summation of primes, the inverse, the comes out to be log n. So the time complexity is n log n when we start from I equal to 2 and we continue till root n, and j equal to I and we continue, no sorry, when we continue till n and we continue till n. Okay, so now you guys are saying that we don't have to move till n. That's right. So the time complexity now would be, we are considering all primes till root n. So this will become root n.
Yeah. So like,
And
so like considering not considering up to n does not give you a huge
yeah,
plus, because of the complexity out of the log will still remain n. So like,
so this will become p will become root n, right? So this factor becomes log root n. Now what will this become? So this indirectly depends on j, right? Yeah, this depends on j. So if we start at x square and we move till n, so and so the distance is n minus x square, and we are taking steps of x, so this becomes n minus x square into uh this, yeah, if I'm right. So this becomes n minus x square, numerator becomes n minus x square. So it's like it will be difficult to estimate the time complexity, but roughly it will be this, it will come out this way: n minus 2 square upon 2 plus n minus 3 square upon 3 plus n minus 5 square upon 5. I don't think it is around root n log n. It's it's an order of n only.
so like it will be O of n plus O of small o of n plus n log root n or something. Think so.
Okay,
Yes.
so do you guys have any doubt in normal Sieve's complexity, or in this if you start at I square also, it
Yeah,
doesn't.
two doubts. What is smaller?
Okay, normal by
Okay.
normal. Okay,
So yeah, I kind of thought that this
yeah. So this
will
is normal
come.
Sieve
So
for me. Like I just start from 2, I iterate till n, I check if this is a prime, I push primes to this, I start from 2i and I just mark all of the primes false. So it doesn't matter if you just continue this till square root of n, or and start from I square, and yeah, you have to anyways move till n over here. So this sieve and the one that was written previously doesn't have much difference in time complexity. It's kind of same.
No, what is smaller? Big O I know, but what is smaller of n?
yeah. Wait.
Okay,
I'll
small o.
one second.
Okay,
I'll screenshot. So I kind of thought that this doubt would come. I guess you were seeing my Notion ka blog. Yeah. So so yeah, I'll take this. Okay, so the first thing that we have in complexity analysis is big O and small o. So how does small o work? So according to small o, what you have is that a function is a function when divided by another function. If you take the limit to infinity, you get it as 0. So how is that different from big O? Well, in big O we have the condition to be the limit suprema will be less than infinity. Why are we using suprema? Well, not all functions are properly analytic as such, so we cannot just use normal limit. So we have to use lim sub. But if you don't understand what sub means, you can just consider for normal functions that we are taking normal limit with respect to mod of fx by gx. And if that comes less than infinity, then we call f is order of g, which is big O of g. However, if this comes equal to 0, then we call that f of x is small o of gx. So does that clear it out? So this is also represented as equivalent of G, like if is similar to G. Does that clear it out?
Yeah,
I
I
got,
mean, go
uh,
ahead.
Yeah.
I actually forgot what supremum means, so I'd have to look up on that.
Yeah, I mean, I'll give a definition of this in simple words. Like, I may be wrong. Someone can correct me if I'm wrong. But like when you say order, you're not ruling out the possibility that your bound is a tight bound. Like it can be exactly that. By saying smaller, you're saying like it's definitely a strict upper bound. Like it can't be equal to n log log n. I think.
Meaning of small. Hmm. With respect to Suprema, if you want to know what it means, like it's basically like if you have a set and
No,
the
sorry,
least number that is the
I
great.
meant limit superior. Sorry, my bad.
Acha, limit superior. Okay, okay. So limit superior, yeah, I have the precise definition over here. It's basically the least upper bound with respect to a current function which you have, like a current function that we have, such that you are taking a value to that function which is greater than the value while you are approximating the limit. And yeah, so you take the least upper bound of that and take the limit over the entire function. So that will give you limit supreme or lim sub, whatever. Does that clear your doubt?
It does, but I'll have to look up the notation later.
Yeah, so I guess one thing you can do is that all of these are taken from math for CS by MIT. I'll link it after the meet. Like I'll send you the
Yeah, I
link.
also had a second doubt.
Also,
I-
one second. Yeah, so Pratik said the thing like about little o. Yeah, so indeed, little o notation, what we do is that we describe an upper bound that cannot be tight. So, like what he said is basically, did you get his point also? Like, I hope.
yeah, I got it. I got it. Yeah.
Mhm, mhm. Okay. So yeah. Go ahead.
So before this, we
Anything
saw
else?
this code, right, where we are doing j plus equal to I.
Mhm.
That is not Sieve of Eratosthenes, right? In Sieve of Eratosthenes, we do j equal to j times I, right? No, I think
J is equal to
somebody else was sharing. I think it was Amol who was sharing.
Yeah, in his code also this is same. What do we
yeah.
do?
So no. So in original Sieve of Eratosthenes, what we do is J is equal to I square of I. I don't take like because J is equal to J into I makes no sense. So like, do you get
No,
why
no, no.
we are squaring it?
He was talking about incrementing. Like what exactly?
Acha, J
Exactly.
plus this part.
Yes, yes.
Yeah. We have to use this. Like, otherwise it's redundant, right?
No, no, I'm saying equal to j. Uh,
J equal to J times I.
yes, exactly that one.
So you are saying that we start from I square, then I cube, then I to the power 4, and so on.
Exactly.
Uh,
Then won't you just cross off powered primes?
yeah, okay. That will leave too many numbers, right?
Sorry. Yeah.
So, for example, like if you have 6, how do you cross off 6? Because 6 is neither 2 squared nor 3 squared.
Yeah,
It's not a
sorry.
square number.
My bad. Yeah, got it.
Yeah, so what you were talking about will only be suitable for primes of the form p to the power a, p1 to the power a, p2 to the power b, where a, b, all these are even. Yeah. So otherwise you can't solve. So I guess Sieve of Eratosthenes is clear. I'll show you the code when I go into linear sieve and sieving over a range. But like for now, let's discuss about counting divisors and sum of divisors of a given number. Okay, so yeah, my journal is working now, which is nice. Yeah. So suppose you have a number. Suppose you have a number n. Cool. What I now want you to do is that I want you guys to find out how to check for divisors of n. Like I want to know how many number of divisors does this number n have.
Alapan, sorry to interrupt, but like before we proceed to the next topic, I'd like to point out something about the previous one. Yeah, so basically this you have to understand the distinction between the order root and algorithm we did and this one. So like where each one is more useful. So when you need to find out all the primes up till n, then Sieve is more useful because like it will be order log n per log n per element, and like but when you only have like three numbers, three numbers up to 10 power 9 that you want to like factorize or like check if they're prime, what do you think you'll do then? Like obviously we'll use the order root and algorithm because we can't run the order and algorithm then. Like we'll basically be getting redundant information, like things you don't need. So yeah, there's definitely use for the order root and algorithm as well.
Yeah. So as Pratik said, so the order root and algorithm, what we mostly use it for is something which is known as segmented sieve. So what does segmented sieve do? Is basically it optimizes your memory as well as like the space you have to search for. For certain problems, like if you want to find number of primes in between L to R, where R is of the form 10 to the power 12 or something, and L to R minus L plus 1 is of the form 10 to the power 7 or 10 to the power 6, with respect to whatever you consider
No, I think
to
Alapan,
pass in order of.
he said that like for bigger numbers, like we use root n algorithms, not order of root n segmented sieve. Like we had two algorithms to check the primes, right? So if I have a number x which
Acha,
is
okay,
bigger
that
than,
one. Yeah.
so
Ah,
yeah.
okay. Yeah. Sorry. Yeah. That makes sense. Hmm. Okay, so let's now talk about uh, uh, number of divisors of a given number. So, given any number, what we can do is that I can represent the number in terms of primes, right? So, suppose this number is divisible by, these are my primes. So, this is the prime factorized representation of my number. To generalize this, it will be anything from up to certain m a of n. Okay, so if I give you this number, can you tell me what will be the number of divisors of n? Like, speak out rather than writing in the chat. Like, it will be easier for me.
A1 plus 1 into A2 plus 1 into A3 plus 1 and so on till AM plus 1.
Yeah, reasoning. Like, why are we doing that?
Each
Because each factor has so many possibilities for, suppose we need to consider P1, so it has A1 possibilities that the power will be 0 for P1, 1 for P1, 2 for P1 and so on till A1.
Yeah. So total for each P1 with a given certain power, we have how many possibilities? We have possibilities from P to the power 0 to P to the power A1. So all these powers of primes can be present in a certain divisor of D. So the number of choices we have for P1 is independent of every choice. So we add all the possibilities. So we have total possibilities of A1 plus 1 because 0 to A1. And now these two are not independent, these two are dependent. So I will have multiplicative counting with respect to the other primes, and so I'll have similarly a2 plus 1 plus a3 plus 1 and so on. Yeah, so this will give you d of n, which is a shorthand representation for divisors of n. And if you look closely, this is actually a multiplicative function What do you mean by multiplicative function? Well, if you have two numbers, mostly co-prime, then you can represent it as this. Yeah. So that is the basic idea. So like if you have like p to the power LA1 into p to the power A2 should be representable as P1 A1 into D of P2 A2. See, only if these two are co-primes, because if these two are not co-primes, then they're dependent. It makes no sense to have multiplicative form. But yeah, so this is the basic idea. So what if we want to find the sum of divisors of the given number? So again, we have a similar representation for n. We have p1 to the power pm to the power am. And what I now want to find is sum of all these divisors. So what do you think I have to do now? Like I can use the similar idea that he told previously, right? You have to check from 1 to p of 1 to the power a1. Like I have to check cases based on this. So what do you think would be a way to find this?
M nested for loops.
M nested for loops. Yeah, but that is computationally costly, right? I'm not talking about the computational aspect here. Like, just give me a formula to find it. Like
You're asking sum of all
formula.
divisors, yes?
Yes, yes, yes.
Oh, so it would be the GP sum of what you've circled. It would be the sum of that whole multiplied by 1 plus p2 plus also the formula would be p to the power a1. Yeah, this into p to the power a2 plus 1 minus 1 by p2 minus 1.
Can you reiterate your ideal idea for doing this? Like why we are taking GP and why we are multiplying individual GPs?
Because for finding the sum, we need to find the sum of each divisor. So if we take each of these sums and we write it as 1 plus p1 plus 1 plus p1 plus p1 square plus p1 cube, and then if we write 1 plus, so if we see if we try to expand this sum, if we take all the ones and we multiply it to and take all the ones, then we'll get the 1, which is a divisor. If we'll have m brackets as like this, right? So if we take p1 from the first bracket and we take 1 from the rest of the brackets, then we get p1. If we take p2, if we take 1 from all the brackets except for the second bracket, and if we take p2 from the second bracket, then we get p2. So
yeah, so basically you have your divisor of the form certain p1 x1 and x1 belongs to 0 to a1, and p2 x2 if you have, then that belongs from 0 to a2 again. So like the possible way to figure out a formula for all such d's and summing over all of them would be to would basically be sum over all these powers, and that the individual summations will be multiplied, and this will be for p1, this will be for all cases related to p1, this will be for all cases related to p2 yeah, I, where I belongs to like a1 a2 0. Yeah, so this will give you a GP series of the form this. So the effective formula that you have is sigma of n is equal to p1 a1 plus 1 minus 1 p1 minus 1 into dot. Yeah, basically the same thing will iterate all over again, and you will have yeah. Now again, one thing that we can say is that this number this function sigma is again a multiplicative function, because of the like it's evident from the proof that we used to figure out that this works. So this again is a multiplicative function, and multiplicative functions do occur often, and like one of the most important multiplicative functions is phi function, which will come very soon after discussing linear C. Okay, so however, these are these are your formulas related to finding number of divisors and sum of divisors. But what will be an effective way to figure out, like actually compute the sum and number of divisors? Can you tell me any algorithms to find out sum and number of divisors of a given number n? see one thing that should be evident, that again, like if you actually perform this algorithm or whatever, if you want to check for all prime numbers, like if you want to find out like all prime numbers ka powers and then compute this might be computationally non-effective. So like tell me a simple and effective way to figure out the sum and number using your knowledge of the Sieve algorithm that we just talked about. So any ideas?
Can you repeat the question?
Yeah, the question is basically to find sum and number of divisors. So one thing should be evident, that both the problems are computationally equivalent. Like if I want to find the number of the sum of divisors of n, and if I want to find the number of divisors of n, I can do that in the same program within the same time complexity. So if you tell me either of these two algorithms, I can figure that other one. So I want you to tell me like how to find number of divisors of n using the idea of sieve of Eratosthenes that we just talked about. Is the question clear? Like anything, like if you have a completely wrong approach, it doesn't matter. Any ideas? So basically what we can do is we can use an algorithm of the form this. So we are using the same idea of the sieve again. What we are doing is that we are taking num and sum array. So both are computationally equivalent because the time complexity is similar. You don't need to consider the other. So if I just consider the number of primes, what I'm doing is that I'm again iterating through 1 to n. I'm using the idea of sieve. Once again, this should be. So basically, I'm checking out for every number. I'm just adding the number with respect to just incrementing it, and similarly, I'm again incrementing it with respect to the sums. So in case of sum, I have to do plus equal to I because like I have to add it, and just for the num, I just have to increment the count, so that will just give me the number of divisors. So this is a nice example of how to use the basic Sieve algorithm for um, sum and number of divisors. And yeah, so after this,
And yeah, the complexity of the number of divisors and the something is order of n log n and not n log log n, because you can just see check Aju, just can you show the code?
yeah,
There is one slight difference. In C we only ran the inner loop in case of primes, but here we are running it for every I. So it is kind of n by 1 plus n by 2 plus n by 3 up till n by n. So the value of 1, so that comes out to be n into 1 by 1 plus 1 by 2 plus 1 by 3. So it's around n log n. You can just integrate 1 by x to find the complexity for that. Anybody having any doubt with that? No, right? Okay. Cool.
So now let us talk about a few problems with respect to what we have learned. Amul, do you want to take over?
Okay. So we will, yeah. So let me just share my screen. So we will first move to this problem. Yeah. So basically you can read this problem. The problem says Chef doesn't love math anymore. He loves Shasha. She is cute. Chef goes on a date with her. Flowers are boring while numbers are not. He knows that most of all these girls love numbers. That's why he is going to bring a ribbon with numbers L till R written on it. Sasha thinks that the numbers with prime numbers or divisors are special. That's why she is going to kiss boy for each such number he will bring. Now, chef wonders how many times he will be kissed by her. Okay, so the question is, you are given a range from L to R, and you need to, there is a function which is defined for every integer, f of I, which is uh, the number of divisors of I. Number of divisors of I. You need to count the number of I which is greater than L and less than R and has f of I as prime. Okay. So anybody who didn't get this question can ask now. I'll give you a 1 to 2 minutes to think on it.
Mm. I can't exactly. So,
Sorry.
okay, so there's a set of numbers given,
Yeah.
and we have to calculate the number of divisors for each number in that range and find out which of those numbers have a prime number of divisors.
Yeah. Basically, not set of numbers; it's a range of
Using-
numbers. Basically, yeah.
Okay, using that using those formulas, programs.
Yeah.
What we used what we
So the
discussed.
constraints, knowledge of those things are sufficient to solve this. The constraints are L and R is around 10 to the power 12, and the range will have maximum 10 to the power 6 values. So I'll just write down the constraint. L, comma R less than equal to 10 to the power 12, and but R minus L is less than equal to 10 to the power 6. Yeah. So do you have any doubt with the question now? If yes, you can ask now. Also, if anyone has any ideas, you can speak up, right? You can just share with us.
So I'm pretty sure this condition that R minus L is less than equal to 10 power 6 is not needed. Okay, it's needed, never mind.
I mean, we can't do the entire algorithm because it can go till 10 to the power 12. So
Yeah.
starting from 1 to 10 to the power 12 will not
Yeah,
be allowed.
correct. We can't do the naive thing.
No, yeah, we don't need that R minus L less than equal to 10 power 6 condition, I'm pretty sure.
Yeah, your voice is not clear. Can you speak again? Pratik?
Yeah, I'm saying I don't think this R minus less than equal to 10 power 6 condition is needed. You can do better. Like you can do even when this is not the case.
अच्छा अगर R minus L वाला if it's around 10 to the power 10, can we find it?
No, it doesn't matter. It can be as much as 10 power 12 also.
Ek minute, 1 minute. It doesn't matter.
Let me think.
It does, right? Like, what's your like? You can discuss your solution.
अच्छा हाँ complex हाँ
I think R minus L.
मेरा complexity ऐसा टाइप का आ रहा है like हाँ हेलो
हाँ yes,
तेरा आवाज नहीं आ रहा
आर्जो ओके हेलो
हम्म
आवाज आ रहा
हाँ
है
हाँ हाँ
ओके
हेलो
हेलो
हाँ आ रहा
ओके ओके
है।
so yeah Pratik what solution do you have
हम्म,
where we ignore r minus l
I mean, mm, I'll just give a hint so that I don't spoil it. Just there's very few numbers that will satisfy this thing. You can pre-compute them and store them in a vector, then just binary search.
mm, uh, okay so that's like
yeah okay
computing something before solution right like writing a separate code that will run in 10 to the power 12 or is it like not requiring anything at all from
No, not like that. No. So the number of i's such that fi is prime is very small. Like you can store it in memory and calculate it very efficiently as well.
yeah we can pre-compute that and like just use the fact and
okay
yeah
like
do what Pratik said yeah
yeah but that okay we
By the
don't
way, do
want
we have only one test case,
test
or
cases
are there a
it's
number of
around
test
it's around 5
cases?
yeah you can just ignore the test case it's around 5
Okay.
okay so
yes the binary
One
search
thing
thing
that
is
I can
pretty cool.
think of is that um, it'll have to be perfect squares, otherwise the number of divisors will be even.
number of devices will be even
Yeah,
Yeah.
so that's a necessary condition but not sufficient.
yeah
Uh,
It either has to be a square or it has to be a prime.
what
Okay. And that's
okay
So 36 is a square. What are the number of factors of 36?
okay so I
Okay,
think
so yeah, can you open that wherever you've written that in terms of prime powers वाला formula जो था p1 p1 plus 1 p2 plus 1 जो भी.
okay Arjo that was written by Arjo okay Alapan can you share a screen Pratik wants to explain
Yes uh, mm, yeah can you see
journal wala
wait इधर भी लिखा this part yeah
Yeah, so this formula dn should be enough hint for you to solve it completely. We want dn to be a prime.
yeah so what are the only ways how you can have dn as a prime number just think about that and you will get the solution.
I think I got it.
yeah what is it
Tell na.
So the first thing that we have to notice is that it can only be um, a pure power of one prime, because as soon as we have 2, it'll have two numbers multiplied to get dn, and that we won't get a prime that way.
correct
Correct.
And the second thing is that we can't only work with perfect squares, because we can have something like 2 to the power 8, and 8 plus 1 is 9, which is not a prime.
yeah correct
Yeah, so basically even plus 1 has to be a prime.
Yeah
Even like,
So
okay,
will
even
we
is
have
this
to
even.
use Sieve operator things to pre-compute the primes?
Yeah, I mean, you can even skip that. You can like hard code the first few primes because you need powers of primes, right? 2 is the smallest prime, and your numbers are till 10 power 12. So what is the largest power of 2 that you can get? Your basically your E exponent won't go like more than 90 or 100. 92, I think.
हाँ 100 के ऊपर तो नहीं जाएगा. Yes. So like the idea of pre-computing often helps in the in like reducing your time complexity to a lot. Like if you don't want, like you can brute force the cases and like you
Yeah,
can brute
but
force the
Pratik, but if we have a single prime number in the range of L to R, then that will also have divisors as 2, right?
Oh,
Say,
okay, so okay, 2 is also
Yeah.
prime. Never mind. Yeah, so we
uh,
need that R minus L condition. Yes.
so we have to anyhow
Yeah, we
compute.
cannot pre-compute.
Yeah, so like, yeah, so that will fail with n equal to 2. So like, so let me just show you the solution now. So what Pratik said is we have r till 10 to the power 12. So he said that any number I will be of the form p1 to the power e1, p2 to the power e2, and all. So the divisors will be e1 plus 1 into e2 plus 2 and
Amul
all.
to अपना screen share करना.
Okay, sorry. Like, sorry. Hmm. Hmm. Yeah. So the divisors will be e1 plus 1 and e2 plus 1 into up till en plus 1. So yeah, so let me just reiterate this. So I is of this form. So the divisors will be e1 plus 1 up to e2 into e2 plus 1 up till en plus 1. So if let's so what Pratik was suggesting is we will only have one term in this, and e1 plus 1 has to be prime. So what we can do is we can just we will not have, if we just ignore even as a zero. 1 minute. Yeah, yeah. So if we ignore even cannot be zero. If we ignore even as 1, so there will only we will have to iterate only till 10 to the power 6, and just raise every number to the power 2 and 3, and check if it lies in the range L to R. uh, and then we can just check that yeah, it has uh, you can hear me, right? Hello?
Yeah.
Yeah.
Yes, we
Yeah.
can hear you.
Yeah. So what we can do is, if we didn't have even as a 0, even as 1, so we can just iterate till 10 to the power 6, and we can just raise that number to the power 3, 5, and 7, and just check that if it lies in the range this x to the power 3 or x to the power in, and we can just add that. But we can't do that with when e1 is equal to 1. Suppose we so what this a correct solution is, so you have a range L to R. Every number can be expressed, every number x, let's say we have a number x in this range, it can be expressed in the form of 2 to the power p1, 3 to the power p2, up till some prime numbers uh, pn to the power let me just call it kn to the power pn. Cool. So how many ki's will I have that is greater than 10 to the power 6? That will at most be 1, because I have a limit on r, that is 10 to the power 12. So if I have two ki's which are greater than 10 to the power 6, that it will just exceed, the number will exceed the value r, right? So I will have at most 1 ki, which where ki is greater than 1e6. So what I can do is, I know this formula for a divisor of a number. D of x is equal to e1 plus 1 into e2 plus 1 up till en plus 1. So what I can do is, I will just compute this till all the primes which kn minus 1, where k where every sorry, for every prime which is less than 10 to the power 6, because I can pre-compute all the primes till 10 to the power 6, right? So I know all the primes till 10 to the power 6. So I will just compute this for all the primes till 10 to the power 6 and leave this. So yeah, so what I will do is, first step is pre-compute all the primes till 10 to the power 6. Then second, compute the value for every x that is less than equal to r. That let me just okay, let me just say divisor of x is equal to e1 plus 1 star e2 plus 1 up till en minus 1 plus 1, where basically these are all the primes, these are the power of all the primes which is less than 10 to the power 6, and leave one spot for the prime which is greater than 10 to the power 6. So while doing this, we can also divide this we can just divide this number x by all the primes, and if this x is not equal to 1, this will obviously be just 2, and if it is equal to 1, we'll just have to multiply it by 1. So we will get we will get the divisors of every number in this range using this method. uh, Anybody having any doubt here? I will also show the code. You will get better understanding after that. uh, till now, if anybody has any doubt, you can ask. Okay, just let me just show you the code so you that okay, yeah, anyone's asking. Okay.
Yeah, the doubt not related to this, the code you showed before, the optimized code that you said.
What optimized code?
From the website that you were showing, the
Okay, you don't have doubt in this problem, right?
no.
Okay, so can you just ask after this problem, like it will
Yeah, sure, sir. Sorry.
okay, cool. Anybody having doubt in this problem? Okay, so I'll just show the code for this problem. You will get a better understanding after that. Yeah, so yeah, this was the code. So what I do is I just pre-compute all the primes till 10 to the power 6. So I just initialize n as 10 to the power 6. I made a vector for the primes and just pre-computed all the primes till 10 to the power 6. Okay, yeah, this was changed. Okay, right. So now I take L to R as range, like this one, and I make divisors is the array which will store the number of divisors from R minus L. That is, this is the range, right? So divisor of I will be just divisor of L plus 1 will be L plus 1. Like I just store the range and initialize it to 1, and value is the a value for this. So basically what I am doing is for L, I am mapping it to 0, index 0. For L plus 1, uh, I am mapping it to index 1 and all. So yeah, so value of I minus L, that is equal to I. Now I just run a sieve here again for all the pre-computed primes. So I just find the first power that is greater than L for this prime, and I run a sieve after that. I just yeah. So for every factor of this prime, I calculate what is the power of this prime in that number. I divide it. So for that, I just store it as temp is equal to j. That is, j is my number. I am just calculating the power of my current prime in j. So I just divided multiple times, and yeah, I modify the value. That is, value was initially that number, and I increment the count, that is the power. And so divisors get multiplied by this CNT, that is count of the number of this thing. That is CNT, just CNT is prime, power of prime plus 1. After that, I just check the answer. Like if the value is not equal to 1, then there must be one prime which was greater than 10 to the power 6 and have not yet cancelled the number. I just multiplied the divisors more by 2, and yeah, and this way I get the answer. I just check if the divisor was prime because I have already made a is prime array over here. Yeah, so any doubt in this question? Okay, cool. Yeah, and now you can ask your question. What were you asking?
Yeah, could you explain the optimized code earlier to find the number of primes less than or the sum of number of divisors or the sum of divisors?
Number of divisors and sum of divisors. Like the one with the complexity n log n that I explained. Yeah.
I don't remember the complexity.
The code, right? Which where I was using. Okay, let me just write the code. Right. This code, right? This code, right?
J++ and yeah.
Yeah, this one.
Yeah. So what we are
Some
doing
like
here.
that, some like that.
So what we are doing here is uh, so yeah, so in this loop we are just adding the number of divisors of j. So we just start from I equal to 1 and move till I equal to n, and just check for this number how many numbers are there. But we check that how many j's are there which has I as a divisor. So like we need to calculate the number of divisors for every I, for every j which is in the range 1 to n. So I just iterate over every number and just check like in which j is it contributing, is it there as a divisor. So yeah, so like if you have
Oh, okay, got it. Yeah.
got it right. So yeah, okay.
And what was the complexity over there?
Yeah, this has a complexity of n log n because it's like n by 1 plus n by 2 plus n by 3. This
Yeah,
loop,
okay, got it.
yeah, that right. Hmm.
Thanks a lot.
Hmm. Okay, so moving on. If I think nobody has a doubt over this over here. Okay, yeah. So let's just try another problem.
अच्छा अमूल एक बार sieving within a given range का explicit algorithm भी दिखा दे. Like,
Sieving in a given range.
हाँ मतलब just the typical problem कि L minus R के L to R के बीच में I have to find the primes बस.
Okay.
Like, just have to find the primes.
Okay, so I'll just show you the CP algorithms. I explain the CP algorithms on the code. Okay. 1 minute. So you're talking about this, right, Alapan?
Yeah.
Yeah. So like if we want to find like this is like just similar to this thing only. Yeah. So this thing only. So if you want to find primes in bigger range, like, but the range is 1E7 only, but the values are bigger. So what we can do is we know that like R is this thing. So we know that every number will have a prime divisor. If it is composite, it will have a prime divisor, prime number. Divisor is a prime number which is less than root of x. So what I'm saying is, if a number is composite, it will have a prime divisor less than root x. So using that property, we know that R is less than equal to 1e12. So we can just store all the divisors till root R and mark all the numbers in this range as just cancel out all the numbers. So we will indirectly get the we will indirectly get primes left afterwards.
मैं एक बार कोड लिख के समझा देता हूँ actually.
This is a sub part of the problem we just did, right?
Yeah.
Yeah.
Yeah, I think Alapan, it's not necessary. We are already getting
late, already running late.
Yeah. So yeah. Okay. So we will just try the another problem.
Hmm.
Okay. So yeah. Yeah. So I will just explain this problem. This is a very simple problem. Uh, so basically, you have a numbers from 1 till 20 million. I think 20 million, right? Yeah. How many zeros are there? Yeah, 20 million. So 2 into 10 to the power 6. F of I is some number in this range, is equal to yeah, is equal to number of prime factors. So basically if I have 15, so it is 3 into 5, that is 2. Now if I have 8, it is 2 cubed, so I will just take it as 3. And if it has 24, so it's like 2 cube into 3, so this has 4. So f of I is number of prime factors. uh, you need to sort this array based on this value. Just that's it. Yeah, so I think this is right, quite obvious, right? Anybody having any issues with this? Like, I will explain the code definitely, but also you can just tell me the how will you approach this problem. Like, yeah, it's you all got the question, right? I have numbers from 1 to 10 to the power 6, 2 into 10 to the power 6. I need to sort them. There is no input in the question. You are explicitly given, okay, no, there is input, like I have to mention the value, just but ignore this. The question is one you have numbers from 1 to 2, 10, 2 into 10 to the power 6. You have to sort those numbers, and each number has a value which is the number of divisors it has, and the sorting has to be done on based on this, like in increasing order based on this value. So let's say for example, let me just show you for first 10 numbers. So I have 1 2 3 4 5 6 7 8 9 10. The value of this will be 0, it will be 1, it will be 1, it will be 2, it will be 1, it will be 2, it will be 1, 3, 2, and 2. So after sorting, the array will look like 1 2 3 5 7 4 6 9 10 8. So you just need to sort this array for, yeah, you just need to sort it like this. Yeah, so what approach will you take?
We can use a vector of pairs where
Vector
the
of,
second element would store the number of divisors or whatever that was, and
Yeah, I
then sort it
mean,
according to that.
that's not
yeah.
the thing we're going for. I mean, yeah, that's obviously we'll do that, but we want a solution for calculating this array using Sieve.
Give an approach like how you can use Sieve and modify it like to.
Wait, can you explain f of I again? Isn't it the same as? Oh wait. Yes, can you explain f of I again?
F of I is number of primes in I. So if I is 8, so 8 is 2 to the power 3. So f of I is 3. If I is 24, 24 is 2 cube into 3, 3 to the power 1. And f of I is 4 for this. It's sum of EIs, sum
Okay,
of
okay, I
E1
got
plus
it.
E2 plus E3 up to AN. Yeah, so I guess I will just explain the solution. Yeah, Pratik, can you just tell me what were you thinking regarding Sieve? Like, what approach?
I would do the trivial one, like go through all primes, and for each j, you additionally also calculate what power j is of I, and then just add.
Yeah, so he was suggesting that only, right? I guess, like the one. What was he suggesting?
He wasn't suggesting anything. He was saying
No,
once we have the array, we can make a vector of pairs and then sort it. So
I
that
misunderstood f of I.
Okay.
But I think we can do that. We can just pre-compute the primes and then the dividing method. So
Yeah,
we
okay.
divide n,
So
but then we'll have to iterate over every single element that way. Will it be feasible?
now we don't want O n square algorithm.
It will be O n root n or O n log n.
I mean, it fits in the time complexity. That's all I know. Like I haven't done the complexity analysis for that.
Okay, just let me explain you the correct solution. Okay, cool. So the question was this, yeah. So it's quite like obvious. Like just I just make n as 2 million plus 1 and just make a vector for it, and I just set because 0 should not was not to be included, I just initialize with a very high value so that it gets ignored, uh, and basically ignored by means it gets after sorting it gets to last position. I move over every I from 2 to n, check if the current divisors for this were 0, I make it 1, that is I itself, and then I just move to multiples of this I and just check what was the power of I in this, and just for to that to divisor of j I add that much. So I think it's clear up till here, right? Like how we constructed this divisor array. This divisor array is basically what f was doing. Like divisor array is like f function. So now, yeah, so we make a vector. So the iota function is, this is a very nice function in C++. It is like it will just make a0 equal to 0, a1 equal to 1, a2 a2 equal to 2, and so on up till the whole size. Basically it will start with this value and keep on incrementing with the iterator, and just assign fill this array. So yeah, I filled the a array with the indices. I wrote a sort function. So basically, yeah, this is a sort function. I just sort the I sort the array, like all a's. I think you know what is all a, but I just explain it. All a is a macro for me, which is like c dot begin from c dot end, and this is a sort function. Yeah, so this is a lambda function in C. You can write this as this thing, or you can write it with like this also. Uh, Sort all a comma cmp, and you can just make a comparator of here, bool cmp, and yeah, so this works and this also works. I like to do it this way because yeah, it's like just store the comparator here only. It's no issues. So yeah, I just check if div I is not equal to div j. I return this. If div I is, I return this flag. Else I return I is less than j flag, and then I just iterate over all the test cases and print the answer. Cool. So any doubt here? Like any part of code that you didn't understand?
So what is the complexity of this? Because we're doing extra computation in the loop, right? Inner loop.
Yeah, okay. So the extra complexity will be, I think, since the n is up to 2 million and this loop will run at most 20 times. So it will be 20 n log n, I guess. So it will be around 2a6 star log. That is just 5. I just let me just write it as 5 into 20, I guess. Yeah, so it's around, yeah, it's around 1 in 9, but it will pass, I think. It does pass. Yeah, but I think
Yeah,
I'm
so
using,
20 will only be for 2, right? For other primes, it's
yeah,
more
but
like
yeah, and yeah, 20 will be just for 2, so I think
हाँ
it,
मतलब इससे कम ही होगा ऑलराइट
yeah, so it will pass, I think. Yeah, it will definitely be not very fast, but it will pass, I think.
इससे फास्टर कुछ हो सकता है
I don't know.
Linear sieve.
Linear sieve.
Okay, linear sieve.
Hmm.
That brings us to our next topic.
Hmm. Yeah. So Arjo, continue.
Hmm. Yeah. Um,
Also, let's just be a little bit fast. Like we are already, I think, running very late.
हाँ थोड़ा fast complete कर देते
Hmm.
हैं. Okay, so till now, what we have talked about is about regarding Sieve of Eratosthenes. What we have talked about is finding primes with an algorithm that works like like basically all primes less than n, and then n by p, which comes equivalent to n log n plus something. I don't know. We can optimize it in several ways, like root n, whatever. But can we make it even more faster? Like, can we compute this in like like it cannot be probably done in less than O of n way. I don't know if there is a strong proof regarding that. But like, can we actually perform this entire algorithm, the entire sieving algorithm, in order of n? So this is the question. So what can we do to figure this out? Let's see. So suppose I have a number n. I have my number n. So what I will do is that I'll try figuring out. I'll try figuring out the like a prime. Okay, so what I'll do is that basically I'll start. Wait, I'll show you the code. That'll be fast. Yeah. Yeah, so here you can see what I'm doing is basically I'm iterating from 2 to n, basically throughout the entire, throughout all the numbers. And I'm maintaining an array of, so what this fill function is basically doing for me is basically putting all the values as false initially. So I am considering everything to be prime in the beginning, just as we did in the original Sieve algorithm. Next, what we do is that we consider that if this is not composite, then this is prime. So it will start with 2 and 2 will be a prime, and then we are good with it. The next thing what we do is that we consider all numbers less than, so we consider all numbers in the form j, such that j is less than the number of primes we have and the number of primes we have yet, and such that prime of j into I is less than. So this is basically the condition for multiplicative. So what I do is that given a prime j, if I multiply any number I with respect to it, like any of the i's, the current I, then it'll be composite, right? So what this part basically does is that for every composite number, this part of happens only once. Like the entire for loop, this runs, like the entire code runs only for one time for each composite number. So whenever I have something of the form of a square or something prime, so if it is divisible, then it will give me then it will basically break my given algorithm, right? Using this, I can prove that, as I told, this entire block runs only once for every composite numbers from 1 to n, and this would give me a relatively much faster algorithm, and the entire complexity for this sieving algorithm will work for order of. So do you get the overall understanding key why it's faster and like why it works?
I didn't understand the algorithm. The J part, what is the J doing, the J loop?
So the
So
J,
I'll first explain like what we are trying to achieve. Like the code will come later. So what we want is we want each number to be like sieve of each number, which can be any function, to be updated only once. So how we do that is, so we want, our objective is that we update sieve of j with I, such that I is the smallest prime factor of j. That's what we're trying to do here.
What does the
J,
break condition do?
So the break condition basically makes sure that we don't iterate over like multiple composite numbers which we have already come across. So basically, if it is divisible, then like I will already count it before, right? So I don't want to again go into the loop.
So basically 2 will cross out only 4 and then 3 will cross out 6. That originally was crossed out by 2 and then again by 3.
Yeah.
Yeah.
So that way every composite is visited once. Okay, I got it.
Yeah.
Yeah, so how we're achieving this is, so for each number, we're only multiplying it by one prime. So we store a vector of primes that we have calculated so far. And let's say I'm at some number I. And I want this I, even if this I is not prime, I want this to update my other things. So, yeah, so we iterate through all the primes and um, yeah, whenever, yeah, I mean, the code is pretty much like better explanation for it than what I can say.
I mean, you have to get the intuition key why we are actually why we are doing this. Like this is the main part. If you
Yeah,
understand,
so
like,
think of that smallest prime factor thing I said. So let's say we have a vector of primes so far. Um, let's say my smallest prime factor is I, so it must, let's say it's P. So the P must be already in the list, right? Of primes that I have. Can anyone say like agree to this?
yeah.
Let's say we're at, okay, I'll start again. Let's say we're at some number I. It can be composite, it can be prime, all right. And let's say P is the smallest prime factor of I. Now I have already maintained a list of primes I've found so far. So P must be in that list, right?
Yeah.
Right. So we want uh, a number q such that q is the smallest prime factor of any number we update. So I'll only iterate through all the primes in the list that are less than p. Because if I go greater than equal to p, then p will be the smallest prime factor of the number I'm saying. Um,
Yeah. Do you get like an intuition behind what is happening here?
Why? Actually, no. Why in this the first line in the for loop, if not of is that will always be true, right? Why are you doing that?
No. See, this part is not outside of this loop, right? So first when 2 will come, then it will work. And then when 3 will come, again this will work. But when 4 will come, already 4 has been made composite, right? When 2 comes, 4 has been made composite. So when 4 comes in this main for loop, it will not go through this if statement. Make sense? See, in the beginning, we have, yeah, so let's just go computationally iterate the entire thing. So when 2 comes, 2 enters this, 2 becomes a prime, 2 goes through this entire thing, and then 4 comes, 4 is composite of 4 is said to be true, and then I exit from here because it's I don't want to continue and make it redundant. So when 3 comes again, it works the same way. But when 4 comes back again, 4 is already a composite number, right? Because during 2's iteration, 4 has already been made true. So we don't go through the prime pushback wala thing.
Wait,
So
during 2's iteration, it exits because of the j less than prime dot size condition, right?
During 2's,
I mean, it doesn't matter.
yeah, like
No, I mean, I don't understand why exactly we're doing the last break condition. Like, what is that?
Okay, so whenever we are doing normal Sieve, we want to compute some function, right? Let's say our function is simply finding out whether or not it's prime, right? So we are expressing our each j as j by I times I, right? And the inefficiency in that sieve is that there are multiple such i's, such that j by I times I is equal to j. So how we're uh, like skipping that part is by fixing I to be the smallest prime factor of j. That's what we want. So here I and j don't have their meanings that they had in the other sieve. Here prime j is supposed to be our I, and I into prime j is what we are like expressing as something times something. So our prime j is supposed to be the smallest prime factor of I into prime j. That's what we mean. That's our goal.
Yeah.
Okay, I kind of get it. Thanks.
Yeah, what we basically don't want is to not have redundancy. Like we don't want to have compute the same thing for composites which have already been computed. So I don't want to go through everything, which I will again go through later. So I want to have this occur only once, which is why I have to make this condition happen. Yeah. So I guess you can ponder over it later after the meet, and like you can ask questions again, like if you have. When we solve the gym problems, maybe later, then I will explain it once in a better way. Okay, so what are its applications? Like we can use it whenever we want to make our C faster. Yeah, just as in the previous problem, we could have used this to make it O of n. But yeah, huh. Now, another pretty cool example for this would be to find Euler's Totient function. So let me tell you what Totient function is, and a naive approach with respect to normal sieve and a faster approach with respect to linear sieve. So what Euler's Totient function is that it says, I think you know these functions, function from the Euler's equation when we were checking for when we talked in the first meet, like Fermat's theorem ka generalization occurs as Euler's theorem. So yeah, so here I will actually explain what how to find phi of m and what is phi. So suppose you have a number n, phi of n, what it denotes is basically all numbers from 1 to n minus 1. Basically, n is redundant again, which are co-prime with respect to n. So you have a range, or 1 to n minus 1, doesn't really matter. And you want to say how many numbers are there in this range such that they are co-prime with respect to n. So what does co-prime with respect to n means? Basically, the GCD of that number with respect to n will be 1. So how many numbers will be there for that? Here we actually see the power of the multiplicative functions to actually figure out the value of phi of n for any number. Like we can figure out a generalization for this. So let me walk you through the ideas. I need you to respond so that like you can also figure out with me, I guess. Suppose P is a prime, based on the definition that I told you, like the number of numbers co-prime with respect to n before n, like smaller than n. What do you think phi of P should be? Any guesses? Like it should be pretty easy.
P minus 1.
Yeah, sure. P minus 1. Now, as I told you, you can get an intuition regarding why this phi function is multiplicative. Again, multiplicative means if you have two numbers co-prime, then you can write them as this. So let's see the implications of that. So suppose I have two primes P and Q, then what should be the phi of this thing? It should be P into Q is equal to P minus 1 into Q minus 1, right? And the other property that you need to know for phi function is that suppose you have a number x and a number p such that p is a prime and p divides x, then this phi function becomes p into phi of x. Cool. So this is your expression. This is all you need to know, like your basis set for understanding phi function for any given number n. So let's try to figure out how we can do that with this. So again, we have primes of the form dot 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 p r a to the power r. Let's see what our phi function will be. So now all these parts, these are independent of each other, right? As in co-prime with respect to each other, right? So I can always use the multiplicative idea over it. So I can always do this, this, dot, dot, dot. Yeah, same thing. So now P1 whole to the power A1 serves as entry point for our this theorem. So what we can just do is that I can take out P1 for all such things, and I'll just have phi of P1, right? Similarly, I will have phi of P2 dot dot dot. Now I can use my first thing that you guys figured out, that for a prime this will be simple as this. So what you will have is basically P1 minus 1, P2 A2 minus 1, P2. Let's rearrange this mess to make it cleaner. What we can do is that we can basically multiply P1 with it, and I get 1 minus 1 by P1. Yeah, more like it. And the same thing all over again. So here I get P1 A1 into P2 A2 dot 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 dot, dot everything. And I have P1 minus 1 by P1, P2 minus 1 by P2 dot dot dot. This is basically n. You have phi of n is equal to n into, for all such primes I, you have P of phi. Yeah. So this is Euler's phi function. Okay. Now I know what my phi function is, but how do I find it out? So why do we need to figure out the phi function? Well, it serves as the phi function is the Totient function is required for the generalization of Fermat's theorem, and like as I told you in the first minute, like this is effective in figuring out, like, yeah, everything that you can, everything where you use that to figure out GCD inverse and everything. Yeah. So a naive approach for doing this would be just to use our old sieve, which ran in the order of O log log n. And the algorithm, unlike some and divisors, will actually run with respect to n log log n as well, not n log n. So it's pretty simple. Again, what we are doing, we are taking the array, we are computing Totient function as I for all given things. We're just initializing it as such. Now what we are doing, we are again iterating throughout the entire thing. And if it's equal to I, so that means the Totient function cannot be equal to I ever, right? So we know that it has to be updated. So if it has to be updated, what we are doing, we are basically iterating again from I to n, and incrementing j with respect to I again, and we are basically subtracting the, yeah. So we are using the idea this and this to figure out how to subtract this and actually get the real Totient function. So this is simpler and slower. So what we can actually do is that we can figure out a much faster method for doing it, which will be basically an application of linear sieve, and that will be of the form, one second, this. Yeah, I have all of the codes in my blog, so I'll post a link if you need to see it. Yeah, so here we are using basically the idea of linear sieve, what we did somewhere around here. Yeah, so this idea. So what we are basically doing is, if it is not composite, we are pushing back to prime. So now we know that if it is a prime, you kind of understand the intuition between linear sieve now. So we will be able to, we'll just consider the part where the Totient function comes in. So with respect to this, since it is a prime, we have the first rule that we talked about, the first theorem kind of. And then if we have co-primes, then we just basically multiply them. And if a prime does not divide a number, then the two numbers, the prime and the other number, are co-prime by default, because prime numbers are nice, I guess. You get what I mean. And if prime divides I, then prime is no longer then the two numbers are not co-prime. However, we have the theorem that this will be phi of x. So basically we multiply the prime with respect to the phi, and basically we plug all of these theorems, or whatever you want to call them, in between our linear sieve approach. So everything else remains the same, even we break after this, just as we did initially. And this basically solves as a faster method to find Totient function. I hope you understood how what is Totient function, and like how we come across the shorthand formula for it, and like its theorems. So maybe if you don't get the code right now, you can maybe look again later. I'll post some links regarding that. Amol?
Yeah, okay. So finally, we have some more problems that we will do on Sieve. Okay, let me just share my screen.
Can you explain something? Is it possible to find the sum of divisors using the linear sieve also?
Yes, but you need something else, another array. I think that will be one of the problems. I'm not sure.
No, that's not that. We have not listed that.
What
Linear.
Linear sieve, can we actually find the sum? Wait, is there any proof regarding that Totient function is a harder problem than? Wait, no, it's same time complexity. Right? Never mind.
Yeah, so yeah, before we go to the problem, I'd like to take another shot at explaining linear sieve. So if everyone has, like, you can open Discord, or Alapan can open Discord and share the screen. I have written 2 codes in hashtag room1text in programming club.
Yeah, one second. I'll share Excel. Yeah,
Yeah.
you can see it. Yeah, this.
So I have renamed the variables so that the p we are considering is a prime, and our m is our multiplying factor. Essentially, whatever number the prime divides, like that number by p is m, supposed to be m. So if you look at the first sieve code, instead of writing it as j equal to 2i, j plus equal to I, we write it as multiplying factor times p. So, is equal to 1. So like line 4 of that, line 3 of that for loop. Yeah, this one. So does this regular sieve make sense to everyone? Like if it doesn't, you can speak up. Or I'll assume that everyone understands. Like it's basically the same thing. There's not much modification in this. Okay, now instead of iterating through our p in our outer loop, what we're doing is initially iterating through our multiplying factor, and we want to multiply this factor with each prime that we can. So like the inefficiency in previous code was that there can be multiple such p's for each m into p. Does that make sense?
Yeah.
Yeah, so there can be multiple such p's. We want to eliminate that. So we'll only have one p for that. So we choose that p to be the smallest prime factor of each number. Like yeah, for every m into p, we want p to be the smallest prime factor that updates it.
Yeah.
So by iterating through all the m's, I want and then iterating through all the p's. So there must be a p that uh, there must be a p in the vector that we have that m divides that divides m. So that okay, yeah, I guess I'll share my screen now to better. It, Okay, who's
Wait,
disabled?
I'll
Yes.
give you sharing permissions. One second. Yeah. Mm, yeah, I think you have sharing permissions now.
Yeah.
Hmm.
Yeah, is it visible?
Yeah.
Yeah, so let's say I have a vector of primes and I have a factor m, and I want to update it for, so then let's say this is p1, p2, and so on. I want to update my function for m into pi, such that pi is the smallest prime factor of m into pi, right? So let's say there is some j such that pj divides m. So let's say it's here. This is the j. So if I multiply m with any number in this area, the smallest prime factor of m into pi would not be pi, right? It would be like it would be pj. Does that make sense? Because these
Yeah.
primes are all larger. These primes are all larger than this one. So if I multiply m, so if I update it for m into pi for any I in this range, then yeah, then the smallest prime factor is not pi, but it's actually pj. So I only want to update it for these values. That's what we're doing by iterating through the thing. So that's why you need that condition where like you can go through the code and convince yourself again, like this makes sense.
Yeah. Okay. Yeah, makes sense now. Thanks.
Yeah, you
Hmm.
get the major point where we are trying to reduce the time complexity, right? Like we.
Yeah, so like yeah, someone who was much more smarter than you thought of that like multiplying yeah, that using the smallest prime factor one is the way to go. And like once we have that this assumption, like once we have made that leap, then this is the code that follows from that, is my point, I guess.
Yeah.
Yeah. Okay. So now I think I can continue with the problems. Let me just. Yeah. Yeah. So this is a problem from a recent contest. So the problem says is, let's just read the problem once. We have two integers x and y. They are adjacent if this condition, if this number LCM of xy upon GCD of xy is a perfect square. So, for example, 3 and 12 are adjacent because LCM of 3 and 12 is 12 and GCD is 3. So, 12 divided by 3, that is 4, is a perfect square. But 6 and 9 are not. So, we have been given an array A. Each second the following happens. Each element A of the array is replaced by the product of all the elements of the array that are adjacent to the current value. So we will have some adjacent elements to AI after 1 second. All those adjacent element, including AI, change their value to the product of their previous values. So Di is the maximum, is the number of adjacent elements to AI. The beauty of the array is the maximum Di value. Now we are given Q queries, and each query is a time frame, and we need to tell at that time frame what was the beauty of the array. So the problem is, I think I've explained it, but let me just explain it again. So like you are a array is there. So there is something called adjacency. Adjacency is we have we say two numbers are adjacent, two numbers x and y are adjacent when LCM of xy upon GCD of xy is a perfect square. So okay, is a perfect square, uh, and we have q queries. Yeah, so yeah, is a perfect square, and there is some update every second. Like we have some array, right? So there will be something like this. So let's say this is adjacent to this, and this is adjacent to this, and these two were adjacent, and this was alone. So after a single iteration, these things, these positions will have a value of a0 star, a1 star, uh, a2 3 4, yeah, a4, and these positions will have value of a2 star, a3, and this will remain a5. So, and the process continues again. We make the adjacent, we find the adjacent elements and update them again, and this continues till w seconds, and there will be q queries, which will yeah. So there is something called yeah, there's something which is called beauty of the array, which is the maximum value of the d which is the maximum value of which is the maximum value of di, where di is defined as the size of this thing, adjacency group, say. Yeah, beauty is max di. Yeah, so I think I'll just explain the solution now. Like I'll let me just give you 2 minutes to solve, to think on this, then I'll explain the solution. 1 minute. 1 minute. Yeah. So I think all of you did got the question, right? Yeah. Yeah, I think most people in the meet might have already solved this problem. So I think I should I go ahead with the solution, right? Nobody has problem with that, or is anybody thinking? Okay, so I'm going ahead with the solution. Alapan, I'm audible, right?
हाँ हाँ
हाँ,
तो
yeah,
बोल
you
दे
are.
बोल
Yeah, okay, so I'm just going
ऑलरेडी
ahead with.
बहुत ज्यादा हो गया था
Wait, I think we have already crossed 2 hours, so yeah. So I think I should go ahead with the solution.
नेक्स्ट हाँ
Okay, so like let's just see what when can two elements. Let's just see when can two elements be adjacent. Cool. So we have this condition, right? That is LCM of xy divided by their GCD is a perfect square. Now, what does this mean? What is LCM? So let's represent x as 2 to the power p1, 3 to the power. Alapan, mute kar do. 2, 3, up till something, this will continue, right? And y will be something like this only, like p1 dash 3 to the power p2 dash, and 5 to the power p3 dash, something on. So what will be LCM of these two numbers? This will be 2 to the power max of p1 comma p1 dash, 3 to the power max of p2 comma p2 dash, and so on. And GCD will be the min. So their difference will be their difference will be 2 to the power absolute of p1 minus p1 dash, 3 to the power absolute of p2 minus p2 dash. Correct. So we can say that this number will be a perfect square. So GCD over LCM will be a perfect square when all these powers are even, right? And when will they be even? When p1 and p1 dash have same parity. By same parity means they are either they are both even or they are both odd. So we get just found this, that two elements will be adjacent when their when the power of their primes has same parity. So power of primes have same parity. Okay, so we got till here. Now what else do we need? We need the uh, size of their adjacency group. So how will we find that? Is uh, we can just check, just let's suppose we are at colored element x. We need to check how many previous elements had same parity of the primes. So what we can do is, for every y, before x, we store we just first break that y into its prime factors and their powers using linear using sieve. So now we have y as 2 to the power p1, 3 to the power p2, 5 to the power p3, so on. And what we will do is, we will just store the product of all the odd powers. So if p1 was p1 was even, um, we will store it as 2 to the power 0. If p2 was odd, we will store it as 3 to the power 1. If p3 was even, we will store it as 5 to the power 0. So for every odd power, we will store it as 1, and for every even power, we will store it as 0, because we are interested only in parity. We don't care what the real value was, right? So um, this way we can just create a, if the sizes were not too big, we can just create a vector. But I think yeah, so I think, yeah, vector will work, because ai is 10 to the power 6. Ai is 10 to the power 6, so this y value, that is this, will be less than 10 to the power 6. Yes, of course. So we can just create mm, a vector which maps number of such y's encountered till now. So we will just do vector of y plus equal to 1 at every I. So we will and then what will be the beauty of the array? Beauty of the array will be maximum vector y for all y, right, at every step. So I think we got everything till now. First we looked at how we find the adjacent elements. That is just checking the parity of the primes. And then we looked at how we will check the size of the adjacent elements list. That is by just storing uh, the y value is for every even power of prime, we store it as 2 to the power 0, and every odd power we will store it as 3 to the power 1. So vector of y plus equal to 1 and max vector will be our beauty. Now what about we can do this for one query, but we have 10 to the power 18 queries. So how will we manage those things? So if we notice one thing, that uh, in the current state, what after the change, what will happen after changing the array? What will happen is the same parity thing, the same the this, let's suppose this was a this one was this was one adjacency group. So if it had this will have all y value same. Let's say it has 3 to the power 1 and 5 to the power 1, 2 to the power 0 as its y value, and value of vector of y was something. Cool. So if that's something is a odd value, then after multiplication we will still get this vector only, this y only. Kyuki, like, because odd into odd is odd, so nothing will change, so this will stay here. But if vector of y was even, what will happen is these powers will get multiplied by 2, and this y will become 1, and basically this adjacency list will get merged with this. But this is after first iteration. What will happen after what will happen at second iteration? Nothing, because already the odd powers have remained the same, so they will remain same throughout, but the even powers have merged with 1. So yeah, so the catch was, we though we have 10 to the power 18 queries, we just need to check till query 1, that is time frame 1, and update the answer then, and after that everything will remain the same. So any questions regarding the logic? Then I will show you the code. Mm, I guess no questions. So let me just move on to the code. What was string? Yeah. So this was the code. So basically, this is just computing the primes. Yeah. This is, yeah. So basically, I'm computing. Alapan, I think we did discuss factorizing a number in log n, right? Did we
Yeah,
discuss? Yeah.
I think there was a problem. Huh?
Okay, we did discuss, right? So basically, I'm just for every I, I'm just calculating prime of I is the smallest prime number that divides I. Prime of I is smallest prime number that divides I. So for example, prime of 8 is 2. Prime of 12 is 2. Prime of 6 is 3. No, prime of 6 is again 2. Sorry, yeah. So yeah, prime of 21 is 3. Sorry, yeah. So I just calculated this. Now, how will this help me? This will help me to factorize every number in log n. So I have created a map. Basically, I could have used vector over here, but I did use map because it didn't affect time complexity that much. So yeah, So this is, I just scan every number. I just for every prime, that is for every prime, I just check the count of that prime. If it is odd, I multiply it. I'm The take array is the y thing. This is the y thing. This is y. I'm just preparing the y value, because if it is odd, I need to multiply the prime with prime over here, and then I just increment the count of y. So this is that y thing. And yeah, so max one is the maximum. I just as I said, that beauty is max one is the beauty of the array at iteration 0, which is just maximum of all the mapped y values. Then I yeah, so max one is at 0 iteration. Now now over here I compute at the first iteration and so on. So for every I created a matter of ll, right? So if for the current thing, the other part was even, then this will just merged into map of 1, right? uh, then it will just merge into a map of 1. So I increment the now value over here, and so this is it, I guess. So if w is the first thing, I just output max 1, and else I output this maximum of the original thing and the current new thing that I have. Yeah, so I guess no doubts here. Moving on to the last problem. Hmm. Yeah, so this problem is again quite simple. So like
Wait, Amol, ये उसमें डाल दे क्या? Like maybe we can put it in the G में डाल देंगे and like maybe discuss it later, I guess. Already बहुत देर हो गई.
hmm, poll ले लेते हैं. Like would you like to do this on your own and bata?
Yeah, like discuss maybe later.
Yeah,
when-
if you want, I can do this now, and if you guys have no problem, like I can discuss it now.
Mhm.
Or do you want it to, you can just write in the chat or anything, anywhere. What's your take? You wanted to do it on now and then, like, have you reached your saturation point?
Can we read the problem before deciding?
Yeah, cool.
Mhm.
Yeah. So we have numbers. Make me what? Yeah. So we all know the superpowers of this world and how they manage to get advantages in political warfare or even in other sectors. But this is not a political platform. So we'll talk about a different kind of superpower. A power positive number is said to be superpower when it is the power of at least two different positive integers. For example, 64 is a superpower. Yeah. So you have to define that list all superpowers. Huh, cool. So basically, the question is um, there is for every there is some again there is a function for every number. So here f of x is equal to if f of x is true when x can be expressed as uh, powers of two different p to the power k1 p1 and p2 to the power k2. It is not prime, like powers of two different numbers. So let's say 64 can be expressed as 8 square and also as 4 to the power 4. So 64 is good. We can just 1 minute, 5 to the power 4. Yeah. So 25. Yeah. So 625. So we can express this express it as 5 to the power 4 and also as 25 square. So 625 is good. But 7 can be expressed as only 7, or we can just check 25. 25 we can express as at 25 square only and 25, but this is not valid. Like we need a power greater than 1. So 25 can be expressed as 5 square and 7 has nothing, no valid arrangement. So you need to calculate all these beautiful numbers which are up till 2 to the power 64. All these beautiful numbers till 2 to the power 64. Yeah, I can just, yeah.
I think we can try this on our own.
Okay, cool.
Yeah, we can do that.
Yeah, so okay, so let me just we have just prepared a new gym. This has a lot many problem, but some of these problems have already been discussed in the meet, so around 4 to 5. So you have around, I think n is 14, so you have around 9 new problems. These are all around div to d slash e level and cde, but yeah, you can approach it because the prerequisites are just topics from this meet and nothing more, I guess. So yeah, you can all you can attempt them all. Some of also these are just picked from the normal code chef and code forces sites, so if you find it difficult you can just check the editorial there. Some of the problems have pretty good editorial. You will get to learn a lot from that also. So okay, any more questions regarding anything in the meet or anything else? Okay, so I'll stop the recording.
हाँ recording stop कर दे